The most important part is here, testing hypothesis. So if you have a sample, if you have a set of sample, if you have a set of data, a data set, right? It's easy for you to calculate the sample mean, right? Which is the average of a certain variable of all observations in that data. We actually learn how to figure it out by using summative descriptive statistics and summative statistics through Excel, right? So that can be easily found. Standard deviation, things like that can be easily found. No problem with that. What we don't know is the population, and actually we guessed them. We make a guess of the population, which is actually tracked by the hypothesis testing. So hypothesis testing reflect your estimate of the population. Then here, what we are actually doing is to test, use our data, use those sample data as the basis to test if the hypotheses are guesses that are too wild. Okay, so what we do is we calculate the t-statistics. Okay, how do we do that? We have standard error, the sample standard error in the denominator, which is, you can consider this as the sample version of standard deviation. So basically, it tells you how much the data in the observation in the data deviates from the sample mean. Okay, and on the top, in the numerator, is the difference between two things. The first is your sample value. Okay, whatever you actually get from your sample, and the second is the hypothesized value, your guess of the population, right? Say if the sample average is 2.5, okay, and you are guessing, well, say possibly it's 1 for this value, for whatever it is, you're making this guess, right? So for that, the difference would be, say, if beta hat equal to 2.5, and beta, which is your guess, okay, equal to 1, and the standard error, which measures the deviation of your data, right? That is say 0.5. In this case, then t-stat is 2.5 minus 1 in the numerator, that's 1.5, over the standard error 0.5, which is 3. What does that mean? That tells you, okay, the sample is this 2.5 as its mean, and also there is this kind of divergence value, right, as 0.5. But here, what you guessed, which is 1 here, right, that is 3 times far away from the sample. Is that likely? That would be very unlikely. Okay, because here, if for two-sided test, okay, if the t-stat equal to 1.96, then the remaining area of this bell-shaped density curve, which this area actually stands for the probability. The probability is only 5%. So 0.025 plus 0.205, that's 0.05, which is 5%. So when we give like roughly 2 times of that deviation level, the possibility of this to happen is only 5%. And here you are even farther from that, right? You're 3 times away, not 2 times away. Then it's so less likely for this observation to happen. If the hypothesized value is correct, then we should refute the hypothesized value. We should consider, well, the null hypothesis in this case that beta for the population equal to 1 should not be accepted, should be rejected, in other words. Okay, so this is the idea. And here we would consider that being, so this 1.96 is also a t-value, t-stat. But here, your t-stat, which is 3, is greater than this threshold, which is 1.96, which means your actual value falls under what we call the rejection zone, which is the shaded area. Okay, so in that case, we should reject the hypothesis. And we consider the population mean should then be significantly different from the original guess, which is 1. Okay. So here we have several conclusions, or I'd like to call it rule of thumb. Those are the gold rules that you should bear in mind. The first one is t-stats. If the t-stat, if the absolute value, why is that the absolute value? Because it could be negative, right? If your t-stat is further away in the other direction, which means your t-stat is, say, -3, which is smaller than minus 1.96, then you are far away here in the tail, in the left tail, then we should also reject the null hypothesis. Okay, so here we were actually talking about question number 2, the method number 2. Okay, and the method number 1, p-value, actually you can ask Excel to produce the p-value as well. And if the p-value is smaller than significance level, then we should reject the null hypothesis. What is the significance level? Significance level is the area of the rejection zone. In this case, if the confidence level is 95%, which is the area, the probability in between, we consider, well, it doesn't differ so much from the mean. So we have 95% of chance that the sample mean is close to the population mean. That is what we call the significance, the confidence level. But the significance level is the opposite. When your t-stats falls under the significance level, namely the rejection zone, we should reject the null hypothesis. Okay, so that's what we do. So if your p-value is smaller than significance level, then we should reject the null hypothesis. If the t-stats is bigger than the critical value, in this case is 1.96, that critical value is the fancy word we call this 1.96, that we call this threshold. Okay, it's actually called critical value. If the absolute value of t-stat is greater than the critical value, then we should also reject the null hypothesis and consider the population to be significantly different from the original guess, from the hypothesis level. Okay. Reject the null hypothesis. to determine the statistical significance. That's a better word. Okay, and the method 3, I will introduce that in regression in the next sets of slides. So let's look at one example. Say, going back to the claim, wages are 6.5, which is the guessed population wages. Okay, and we are to test if it is true. And if we calculate the t-stats to be minus 3.65, and the value should fall to the left of minus 1.96, then we should reject the null hypothesis and make the conclusion that the sample mean is statistically different from the hypothesis value, which is 6.50.